Hello everyone, my topic of final year project is 3D reconstruction from multiple 2D images. The difficulty of 3D reconstruction is that we need to recover the lost depth information. When we take a photo, you can imagine the object is projected to image plane and the depth is lost. However, there are enough information to reconstruct the original model if there are many images taken around the object. In current market, there are many applications using relative technique. They can be separated into two main classes. The first class is handling image taken from normal camera. That means the image does not contain the depth and the position of camera. They are just simple 2D image. My final year project is also dealing with such photos. Another class is handling image taken from depth camera. Those images containing 3D information so that they can generate more precise 3D model. Although there are many products in the market, but we can try to implement this technique in more aspects. Online shopping websites, for example Amazon, Taobao, are very popular nowadays. Many clothing designers and companies try to move their business online to expand the market and lower costs. Shopping websites only allow business to upload some images which are taken from a few perspectives. Using different angles to view an object will have different visual effects. If the customer can view the code with self-controlled angle, that will be funny and exciting. I want to provide a platform for business to upload images of clothes dressed on a person and convert them into a 3D model. Of course, we also allow them to easily manipulate 3D model, for example changing clothes color and eliminate facial features. Also, the website allows customers to view the model in web page without any downloads. Our project is separated into three phases. First phase is environment setup and do research on related algorithm. Also test the algorithm with sample images. Second phase is to build website. We have built a website with a function of uploading images and viewing 3D model in web page. We have demonstration in the end. Actually, we have faced some problems in obtaining product match. We will talk about it later. Our project aims to use existing open source library and program to build an application to handle real problems. Therefore, I don't want to talk too much on algorithm details, but I still need to briefly explain the pipeline of SFM and MVS, which is related to the problem I'm facing. SFM aims to find the camera position orientation for each camera. First, it extracts features points for each image. The feature extraction algorithm can be different for different applications. We use ArcSet algorithm here. Then match features points for every pair of images with a threshold. If the percentage of feature matching is below threshold, this pair of images is recognized to have large orientation between. Then generate checks, which means the feature point have existed in which image. Finally, we can construct sparse point count which include camera position and orientation. MVS is to generate a dense point count and convert it into a mesh. We know the position and orientation of camera 1 now. We can generate a weight by a pixel. It is sure that the 3D points of this pixel must lie on this way. We can project this weight into another image plane and get a epipolar line, such that we can guess which pixel on this line is the 3D point. We can generate another way and find the intersection point, such that we can guess the depth of this point to image plane 1. If there are 5 views, guess the depth and 3 of views agree on same depth. This point will output to dense point count. Our website workflow is separated into two phases. I will explain the reason later. In phase 1, user upload images to website and send to server. Server is implemented in Node.js because it is simple to build prototype. Then server uses OpenCV4 with SFM module to generate sparse point count and gives it to OpenMVS to generate dense point count. Server will display the point count on website with vv.js, which is a JavaScript library to load 3D model on web page. In phase 2, if user is not satisfied with the result of dense point count, it can restart phase 1 again with different images. Else, start reconstructing the mesh, refining the mesh and texture mesh. Texture mesh is a complete 3D model. Owner and customer can see the 3D model on web page. Testing, we are facing two main problems. First one, result is too unpredictable. As mentioned above, the first step of SFM is to extract features and then compare with other images. The lighting difference and out of focus seriously damage feature extraction. We will match feature points for each pair of images. If an image have matching below threshold with all of other image, this image will be discarded. Too many images discarded led to a failure of SFM to increase matching and prevent discarding. The orientation between cameras should be small. Even if SFM succeeds, many feature points, no image is discarded. That also means estimated camera equals to the number of images. Average component size of checks is good. Output of MVS may be also bad. The white figure is a good example of corrupted dense point count. We can see that there are 4 faces, but they are not perpendicular to each other. This kind of corruption is difficult to detect by machine. That's why we use two-phase workflow to let users evaluate the dense point count instead of machine detect corruption of dense point count. The main problem is the quality of source images. We can provide suggestions to users depending on SFM results to relieve this problem. For example, estimated camera is less than number of photos. We can suggest the orientation between angles should be smaller. Also, we can try different libraries with different algorithms to see if there is a better quality of output. In problem 2, computation time is too long. With 99 images as input, the whole process of SFM and densify point count takes almost 2 hours. Our approach to boost the computation time is to downsample images. In below table, we can see the consuming time is far less than original image. There is an interesting fact. Downsample image also help to eliminate noise. In future plan, we will continue to test other algorithms and choose one with better performance. Also, we will continue to test the threshold to evaluate the performance of SFM and give suggestions to users. We will start implementing the manipulation function in next semester. This is our website prototype. We can log in first. User can create new project by uploading images and choose downsample weight. When the project is completed, there is a dense point count to let user evaluate, but it needs a bit longer to know so. So here we have a point count version preloaded. If the user is satisfied with this point count, they can click Start Mesh button, and it will start mesh. And when the H2 is complete the texture mesh, there will be a status mesh here, and we can click inside to load the object. But it also needs time to know, so there is also a reloaded object. Yeah, that is the complete model with texture and mesh.